Hi, I'm Brian Prier, tutoring high school physics. Today's topic, the Doppler Effect. The Doppler Effect explains why, as you hear a police car coming towards you, the siren sounds higher in pitch than when you hear the police car heading away from you. So here's what happens. If you have a stationary sound source like this one, the sound waves are going to be more or less equidistant from each other, moving outwards in a circular fashion. But what happens if that source is moving? That's the Doppler Effect. In front of the source, the sound waves are going to get bunched up, and behind it, they're going to get spread out. So what does this mean for what you hear? Well, in front of the object, the bunched up sound waves result in a shorter wavelength or a higher frequency. This also results in a higher pitch. Behind it, however, the sound waves are going to get spread out, which results in a longer wavelength, which results in a lower frequency or a lower pitch. So that's why you're going to hear a higher pitch as the police car comes towards you and a lower one as the police car heads away. We can actually calculate the observed frequency when a Doppler effect is happening using this equation. The observed frequency is equivalent to the speed of sound in the medium that you're hearing it, plus or minus the speed of the observer, divided by the speed of sound, same speed of sound as up here, plus or minus the speed of the source, all multiplied by the frequency of the source. A useful figure to know for this particular equation is the speed of sound in air, which is 343 meters per second. So what about these plus minus things? How do you figure out which one you're going to use? Well, simply refer to this chart. So for the numerator, you're going to be working with the observer. So if the observer is moving toward the source, then you're going to add the speed of the observer. So speed of sound plus speed of the observer. If the observer is moving away from the source, then subtract. For the denominator, if the source is moving toward the observer, then subtract. If the source is moving away from the observer, then add. Okay, so let's work through a problem. Let's say that we're in Venice and we have two gondoliers. One of them steals the trumpet from the other and gets away on his rocket-powered gondola traveling at 43 meters per second. The other, realizing this, starts his rocket-powered gondola and travels after him at 53 meters per second. This causes a broken tuner in this guy's gondola to fall on the floor and start playing a sound at 425.33 Hertz. The guy who's making getaway with the trumpet tries to tune the trumpet to this particular sound. Now, when you're tuning a trumpet, you want it to tune to the sound of a middle C, or 440 Hertz. Question is, will this guy successfully tune his trumpet while making the getaway? Well, he might not successfully make a getaway considering he's moving slower, but still, let's see if he can tune the trumpet. So our observed frequency is equivalent to the speed of sound, in air this time, because they are in air, meters per second. And so let's see, the observer is moving away from the source. So that's going to be minus. So minus our speed, which is 43 meters per second. On the bottom, we have the exact same speed of sound. And the source is moving toward the observer. So we're going to subtract our 53 meters per second. The observer is getting away from the source is desperately trying to catch the observer and get his trumpet back. And so we're going to multiply all of this by the emitted frequency, which is going to be 425.33 Hertz, the original frequency of the tuner. So let's do the subtraction, and we get on top 300 meters per second divided by 290 meters per second on the bottom, still times our original frequency. And if you run through all the multiplication, you'll find out that our observed frequency is in fact 440 Hertz. And given that our thief is capable of playing the trumpet and piloting his rocket gondolier at the same time, he will successfully tune his trumpet to the sound of a middle C. Alright, to recap. The Doppler effect is what happens when you have a moving sound source. The sound waves in front of the source will be bunched up, the sound waves behind it will be expanded out. The bunched up sound waves will have a shorter wavelength and therefore a higher frequency. The ones that are spread out will have a longer wavelength and therefore a shorter frequency. We can calculate the observed frequency from the Doppler effect using the following equation. The observed frequency is equivalent to the speed of sound plus or minus the speed of the observer divided by the speed of sound plus or minus the speed of the source, all multiplied by the frequency of the source. To figure out how do you do plus minus, on top, if the observer is moving toward the source, then add. If the observer is moving away, then subtract. On the bottom, if the source is moving toward the observer, then subtract. If it's moving away from the observer, then add. Alright, that's all for now. Again, I'm Brian Prier. See you next time.